and welcoming this really exciting panel. And I'll turn this now. I'll turn this now over to Greg. So, Greg.
All right. Well, thank you very much for having all of us tonight. We're really excited to talk about the role of advanced nuclear power as we address the issue of climate change and decarbonization. And so the first thing I want to do is, if everyone could at home and in the room here, scan the QR code. There's a little poll that we want to take that'll kind of level set where everyone is in terms of their knowledge of nuclear energy. And so I'll talk for a minute while you all log in and use your camera and scan the QR code and take the one question poll. You know, we in the US have set out very ambitious goals for decarbonization. You know, reducing emissions in the electricity sector to zero by 2035, eliminating emissions across the whole economy to get to net zero by 2050. And a big part of that is going to come through electrifying as much as we can and decarbonizing the electricity that we have. And so one of the primary ways that we're going to do that is through nuclear energy. And so that's what we want to talk about today. And what are the opportunities, what are the challenges of building out nuclear energy and especially advanced nuclear over the coming years and coming decades. I want to turn to each of our panelists to start and kind of talk about what it is they do and their role in this space. And so Dr. Kathryn Huff, as mentioned, is the Assistant Secretary for Nuclear Energy at the Department of Energy. Do you want to kick us off?
Yeah, more than happy to. I'm really excited to be here. I can tell you're all very smart people because you're deciding to spend your evening talking about this really important topic. So thank you. I am fundamentally a professor. I was a professor at the University of Illinois in Urbana-Champaign in nuclear engineering and was called to come and do this excellent, and I mean actually called to come and do this excellent position leading the Office of Nuclear Energy in the Department of Energy for the Biden administration. It's a real honor because it puts me in a position to oversee a great deal of research and development that supports the continued operation of our existing nuclear fleet through modernization and advancements in their digitization and advancements in our understanding of their operations and maintenance, to help build advanced reactors through cost-shared awards to companies like TerraPower, through direct help with research and development that our national laboratories can assist with, that can accelerate licensing and can support the fact-based assessments that, for example, the Nuclear Regulatory Commission will need to do. And can develop new, technologies in general. It's part of my office's remit to ensure that we have a secure and sustainable fuel supply and fuel cycle. This includes both the front end of the fuel cycle, where we require a secure capability to enrich uranium and to, supply fuel to the nuclear fleet, and on the back end, where we explore opportunities to safely manage and sustainably manage spent nuclear fuel. And finally, and one of the most exciting parts of my job, is a priority in focusing on international nuclear energy cooperation and its expansion abroad. Dr. Isaac said, we do have peer nations around the world that are, competing on the world stage with regard to leadership in this technology. And it is great that it's part of my job to ensure that the United States can continue through R&D and scientific leadership to maintain that capability through expansion of our nuclear energy cooperation. So that's, in a nutshell, what we do in the Office of Nuclear Energy. It's just down the road at Forrestal, and we have oversight over Idaho National Laboratory, which is our flagship nuclear energy laboratory, but we do work across all of the national laboratories across our country. So pretty great stuff. Thank you.
Excellent. Thank you, Katie. Can we put the results of the poll up now? Oh, it's not there? Okay. Well, no. We'll come back to that. Oh, it's there now.
Maybe refresh.
All right.
Ah.
So
Hmm.
the question was, how much do you know about nuclear energy? Looks like we've got about a third Dr. Oppenheimer's, a little bit more Homer Simpson's, and then about a quarter are Dora the Explorers. And so that's a really good range of expertise and knowledge about nuclear energy. So I think that puts us in a good place to really, kind of talk more deeply about some of the areas and talk a little bit at a higher level about some of the others. So Josh, you're the Senior Vice President at Third Way for climate and clean energy. Talk about what Third Way does and what your role is.
Sure. And thanks so much for having me. And it's a great panel and conversation to be part of. So Third Way is a multi-issue think tank based here in Washington, D.C. And we work with policymakers like Dr. Huff and others throughout the federal government and in Congress, companies like TerraPower and others, and then NGOs like Aspen Institute, and conduct our own original research and advise on the direction that the country should take and pragmatic, bold policies to get there on key issues. As a multi-issue think tank, we look at national security and how can we ensure that the United States remains strong and supports our allies and strengthens democracy abroad. We have an economic program that looks at how do we ensure that there is opportunity from the middle out across the entire country, a social policy program that looks at a lot of the contentious issues and tries to find solutions that are broad and bipartisan, and then the climate and energy program. And our program takes the view that the United States both is, historically the largest emitter of carbon pollution in the world and the second largest emitter today, just behind China and roughly, far ahead of Europe now, but close to where they were a little ahead of them historically. And we have an obligation both to decarbonize because of the emission that we're producing now, but also because of the legacy. And as Greg alluded to, we have a large percent of emissions and growing percent comes from the transportation sector, which we need to electrify. And the second largest is from the power sector, which we also have to decarbonize at the same time. And so there's an enormous challenge. The Biden administration has set out some very ambitious and necessary goals. Getting the power sector clean and operating on entirely clean energy by 2035, and having our entire economy at net zero, meaning that any carbon emissions that continue to be produced are canceled out by an equal amount of carbon that we remove from the atmosphere through technologies like direct air capture. About 10 years ago now, in 2013, as we looked at an earlier version of this landscape and said, how are we going to continue to provide the electricity that this country needs, produce more of it, because at the time we were hoping electric vehicles would get to the place they are today, and make sure it was all clean, and make sure it's as reliable, if not more reliable than it is now. And as we looked at the landscape, solar that was emerging, as wind that was emerging, the potential for long duration energy storage batteries, and the nuclear fleet that we had in operation at the time, 20% of our power, the largest amount of our power from clean energy comes from nuclear. We realized that we needed to not just keep the nuclear fleet that we had operating, but we needed to find a way to create a whole new generation of support from a policy perspective, a whole new generation of advanced reactors that could provide electricity, that could help provide the electricity electric cars would need, and a whole bunch of other services, which I think we'll get into tonight, to address the climate challenge, energy reliability issues, and help ensure that we had affordable energy. And so since then, we've been working on that in a variety of policies, which we will, I'm sure, get into as the conversation goes on.
Excellent. Thank you, Josh. And Jeff Navin, you're the Director of External Affairs for TerraPower. Talk about that role and what TerraPower is doing.
Yeah, so TerraPower is an advanced nuclear reactor developer. We're based in the other Washington, in Bellevue, Washington. We were founded a little over 15 years ago by Bill Gates, and the founding of our company came out of a conversation that he had with a collective group of experts, futurists, looking ahead to the future, and he asked this question: what are the technologies that we are going to need to have to solve the dual challenges of global energy poverty and climate change that aren't going to come to the market unless there's some intervention and something happens. And they very quickly got to, we need nuclear power, and nuclear power is ripe for innovation. It's ripe to sort of take a look at how we've been doing things and do things differently. And if you know anything about Bill, you know an innovation challenge is the kind of thing that keeps him going. So he founded TerraPower, and we've been working on that question and that challenge ever since. We have a project that we're doing in partnership with the Department of Energy through the Advanced Reactor Demonstration Program to build a first of a kind advanced nuclear reactor. We're doing it at Kemmerer, Wyoming, which is in the southwestern part of the state. And we are building that plant just across the road from a coal plant that's slated to be retired. Our reactor is different. It's different than the way that the current fleet generally operates. I will keep this at the door of the Explorer level because I have a degree in English, and if there's no chance I'll get too technical for you, I promise you. And if I make mistakes, Dr. Huff will jump in and point out where I've done so. So typical nuclear reactor is actually somewhat simple. Like a coal plant, it creates heat. And uses that heat to generate steam and spin a turbine. But instead of burning coal or burning gas, it uses the fission of uranium atoms to create that heat. It does a very, very good job of creating that heat. And that's how almost every nuclear reactor works. Our reactor does something very similar, but it differs from the conventional reactors, the one down the road at Calvert Cliffs, the ones that you see on The Simpsons in a few key ways. One is it's actually real. It's not made up from a cartoon. But so first of all, our reactor is a lot smaller. So it's 345 megawatts. The big reactors that Dr. Isaacs talked about, the ones that are coming online in Georgia, they're 1,000 to 1,300 gigawatts. So we're a third or a fourth the size of those reactors. Makes it a lot smaller, easier to finance. The overall cost of the project is smaller. And it's a nice size of a replacement for a coal plant, which we think is a really important part of where we're going to see our market grow. The second piece, and perhaps the biggest way that we're different, is that every nuclear reactor operator worries most about dealing with heat, right? The fission reaction gets very, very hot, and you have to actually actively remove that heat from the reactor core, or else the fuel rods will melt together and then melt down through the base of the reactor, which is where that term comes from. Every reactor operating in the United States uses water as its coolant, and it works very well. But there are some limitations to water. Largely, it's boiling point, right? The boiling point of water at 100 degrees C means in order to keep that reactor cool, you have to constantly pump cool water into that core and take the hot water out. So you can also make it a little easier by pressurizing it to raise the boiling point. So that means in a lot of these reactors, you're operating at high pressure, right? And then you're making sure, what a nuclear operator is doing most of the time is making sure that coolant, that water is constantly flowing over the core to allow the reactor to continue to operate. We're not using water as our coolant. We're using sodium. Sodium's an element. It's a metal. At room temperature, it's a solid. You heat it up a little bit and it becomes a liquid. The boiling point of sodium is 882 degrees Celsius. So it can't boil off. Our reactor sits in a pool of sodium, and the sodium just uses natural convection to remove the heat. That means we can operate at atmospheric pressure. From an engineering point of view, it's a lot easier to design. And our reactor is kind of boring. It's just fuel rods sitting in a pool. We don't have auxiliary pumps. We don't have backup safety systems in the same way that a large light water reactor does. What does that mean? It means that we're using things that are inherently safe, and our designs can be much simpler, and those simpler designs actually bring down the cost. The third thing that we do that's different is instead of just using that heat to generate steam and spin a turbine, we're taking some technology that's been used in the concentrated solar industry, and we're using that heat to run a very large energy storage system run by molten salt. We heat up the salt, keep it in a hot tank. When we need extra energy, we push that through the system and use that to generate electricity, and then it goes into a cool tank. What does that mean? It means we can store up to 500 megawatts of electricity for 5.5 hours. We have a nuclear reactor that can go from 40 megawatts production up to 500 megawatts. This is really relevant in Wyoming, and it's becoming relevant everywhere because Wyoming has a lot of wind power and their bulk of their system is operating on wind. But when the wind stops blowing, they need something to be able to come up, ramp up, and to meet that production. The easiest way to do that right now is to use gas, which works really well, except it emits carbon dioxide. So we are going to build the first truly carbon-free baseload power system that can ramp up and down to meet the needs of the grid as we're putting more and more renewables onto the grid. We view Natrium as an opportunity to be that last set of building blocks you need to get to 100% clean energy system. So we're really excited about the project. We expect to break ground hopefully this fall. We're just waiting on a couple of environmental reviews to be complete. And partnering again with the Department of Energy, who've just been terrific. And so really happy to be here.
Excellent. Thank you, Jeff. So let's step back for a minute and talk first about these goals that we're trying to meet. A few of us mentioned these decarbonization goals. I guess, Josh, can you dive a little bit deeper into, the electricity system specifically, and then what are some of the challenges that you're seeing in decarbonizing the electricity system, especially as more people are driving EVs, as we're electrifying more things and demand for electricity is going up?
So today we use a wide mix of fuel sources for electricity. We use natural gas, we still burn some coal, we use nuclear power, and then we use wind and solar, which as both Jeff and Dr. Huff mentioned are variable source of electricity. When the sun is shining, we're generating a lot of electricity. When the wind is blowing, we're generating a lot of electricity, but there are often times when one or neither of them is happening. And so we have to balance the entire system so that we have all of the electricity we need every single second that it is needed, where it is needed. That's a challenge enough on its own. And we want to eliminate all of the electricity that is currently being generated by natural gas or coal if that carbon isn't captured and stored, removed from the atmosphere, prevented from getting into the atmosphere. The challenge is there's a significant amount of the electricity we still use today that is coming from those emitting sources. And as Greg mentioned, the goal is to get to roughly about 80% of all new vehicles by 2030 to 2035 being electric. So as many electric vehicles as there are on the road today, plugging into the charging infrastructure that is still growing, we're going to have an enormous amount of additional demand to also add to the grid, all of which needs to be clean by 2035 at the absolute latest to meet the Biden administration's correct and ambitious goals. There's an enormous challenge there. A lot more infrastructure needs to be built out. One of the projects that my organization runs is something called Decarb America. It's a website where we've done a lot of modeling of different scenarios. If you build certain amounts of this, how much electricity can it provide? What are the costs? So we can get a sense of what is a realistic set of aspirations that we want from a policy perspective and from an infrastructure and building perspective to achieve. Here's the challenge. To meet what we anticipate the electricity demands will be by 2050, which is the long-term target, including the growth in electricity, we're going to have to build approximately 115 gigawatts likely of new nuclear. That's an enormous number of large light water plants like the 3 units that have come online over the last 4 years. In addition to that, under the estimates that we modeled out, which include all clean energy sources, we're going to need to build 10 times the energy storage we have today. 200,000 miles of new transmission lines, because particularly with wind and solar, where we generate the wind, where we generate the solar power is not anywhere close to the cities that consume most of it. So a lot of new transmission lines need to be connected. And as many of you, I'm sure, have seen in newspaper and online stories, it is very difficult to build transmission in the United States. And we're going to need to build a lot of renewables. So we face an enormous set of infrastructure, regulatory and capital challenges to get where we need to go, and some pretty important and tight deadlines, both to meet demand needs and also climate imperatives that are very unforgiving.
Thanks, Josh. So it sounds like we're going to need a lot of money to go into the system to be able to build all these things. Dr. Huff, you're appointed by the president to be the Assistant Secretary for Nuclear Energy. So you're sort of a direct descendant of Dr. Oppenheimer, since DOE was the Atomic Energy Commission, which was the Manhattan Project. And so that's some big shoes, or maybe a hat to fill. Can you talk a little bit about the Biden administration's plan? Obviously, last year we saw a number of bills, or over the last 2 years, a number of bills passed by Congress that the administration is now enacting and putting money out the door. How are those impacting the decarbonization of the grid? And then how are those impacting how you're thinking about the Office of Nuclear Energy and what DOE can do in that space?
Yeah, I mean, the last couple of years have been incredible in putting resources into the hands of the Department of Energy, our counterparts across the various climate-related agencies, and in the hands of potentially industry. Ideally, the United States federal government's budget should not be the sole investor in this expansion. It's actually that it should incentivize much more private money, right? A single American taxpayer dollar should create an incentive for tens and 20s of private dollars for investment. And I think we are beginning to see that from the Inflation Reduction Act and its production tax credits and investment tax credits available soon for some energy technologies like nuclear, available already for some others. Those tax credits are in a place to make sure that there's an economic reason to build out new infrastructure like was just described. In the bipartisan infrastructure law, we have billions of dollars to support continuing the economic operation of our existing nuclear fleet that may be economically challenged by the markets they're in. And if shut down, would be replaced, no doubt, by natural gas in the near term, because we don't have time to build as much renewables as it would require to replace some of the gigawatt scale plants. So to avoid those shutdowns, the Civil Nuclear Credit Program was rolled out. There's also $2.5 billion to support the cost share projects like TerraPower's Natron reactor, the X-Energy 100 reactors, and a bunch of other reactors, of course, under my office, happen in my annual appropriations, which have continued to grow over the last few years in the Office of Nuclear Energy. All of these provisions, all of these incentives are beginning to show a shift in the customer base that we see in the procurement and order book around nuclear power. We're seeing existing nuclear power plants beginning to be more interested in continued excess subsequent license extensions, so they can continue to operate longer if they apply to the NRC for another 20 years of operations. And we're seeing a lot more appetite for that, even in some of the markets where we expected some of them to be more economically challenged. And we're seeing a lot of interest from companies like Dow, right? Dow Chemical has partnered with X-Energy, another advanced reactor demonstration project, to produce high temperature heat in Texas for their, Dow Chemical activities, right? Because you sometimes need direct heat and not electricity to fuel your activities. And so nuclear has an important role to play there, which I know we'll dive deeper into later. But those provisions are really critical, and having those resources available, plus, it includes things like extra authorization for the Loan Programs Office, right? In DOE, we're able to execute some loans to some of these capabilities. We have $250 billion of loan program authority to apply to clean energy projects like nuclear power plants or nuclear power plant factories. We would really like to see nuclear power plants being built more like airplanes than airports. Small, like Jeff was describing, is a smaller capital investment. It keeps you away from some of those over schedule, over budget mega project challenges if you get small enough and you can start assembling them rather than constructing in a stick-built fashion on site. So There's a lot to say about this, but I think fundamentally it comes down to the incredible challenge of our climate goals. Getting to net zero by 2050 is going to require, as you already said, our assessments agree. We think it's going to require between 1 and 200 new gigawatts of nuclear power in the United States. We're not alone. The International Panel on Climate Change in 2018 said that the average scenario that they calculated to stay under 1.5 degrees C is about 2.5 times the amount of nuclear across the world as we currently have today. The UNECE said the same thing, 2 or 3 times. The Nuclear Energy Agency, the IAEA, the IEA, all of them have assessed really similar numbers across the world if we're going to meet our 2050 net zero goals. So I think the challenge is extremely clear. Inside DOE, of course, we see the challenge of all of the firm clean energy we have to deploy. And from our assessment, it's between 550 and 770 new gigawatts of clean, firm power that we have to deploy, including long duration energy storage, et cetera. Carbon capture on our existing fossil plants and whatnot. Plus, within that 500 to 770 is 1 to 200 gigawatts of nuclear, which would double or triple what we have now.
Excellent, thank you. Now, Jeff, you're a recovering policymaker. In your previous life. You were the chief of staff for the Department of Energy. We're talking billions and hundreds of billions, and I think I heard you say the word trillions of dollars. What is this policy? This policy shift mean for companies that are looking to develop technologies like TerraPower is, that are looking to put steel in the ground?
Yeah, when Elon Musk was building Tesla, you heard all the time people say there's nothing harder than starting a car company from scratch, right? I would argue, let's put a new nuclear company up on that list of things that are also pretty difficult. A lot of engineering and science has to go in to developing your concept. Right now, TerraPower, we have about 500 engineers working full time, both in-house and through our contractors, on our reactor design, getting it ready to have our license submittal to the Nuclear Regulatory Commission. That is just to get the thing ready to go to the NRC so that we can finalize our plans and get it built, right? It takes a long time. Like I said, TerraPower has been around for 15 years. We hope to have our reactor operating by 2030, so we still have quite a ways to go. If you go to any venture capitalist and say, we're going to need a handful of billions of dollars, and in 20 to 25 years, we might have the ability to start returning a profit or a return on that investment, you're not going to do very well, right? So the first of a kind nuclear is really challenging. You can't just kind of, go work in your garage and try to throw a reactor together and see how it works and take it to the market, right? So overcoming that first of a kind challenge is difficult. And I think that's why the Congress said, we're going to partner with, via DOE to help offset the cost of that first plant. It's not a demonstration plant, and it's not a prototype, it's not a pilot, it's a full-scale, actual commercial scale reactor. But there are things that we have to do, like have a facility to fabricate our fuel rods. That's a one-time cost. We'll be able to sort of use that as we go forward. Licensing is another big one, right? You have to do that for your first one, and you can then sort of, get some of that money back as you build subsequent plants. But getting over that first of a kind hurdle has been something that we just haven't been able to do on the non-large light water reactors. So that's where ARDP comes in, and it plays a really big role. We do have a utility partner in Rocky Mountain Power PacifiCorp, which is will own and operate the plant when it's operational. We're talking to them already about potentially looking at additional coal plants that they have slated to be retired, that we might see if natriums can be in places there. But getting over that first hump is hard, and so that's what the ARDP is really designed to do.
Excellent, thank you. I want to turn now to and we touched on this a little bit, of the difference between advanced nuclear reactors and kind of the nuclear reactors that we think about when we see them on TV or drive past them. So Dr. Huff, can you talk, I guess, more broadly about what the differences are between kind of the typical light water reactor and the kind of the slate of all the different advanced nuclear reactors that are being developed and starting to be built now.
Yes, and I'll time myself so I don't give you an hour-long lecture. Jeff did a fantastic
I'll bring
job describing a sodium-cooled fast reactor of this new generation that captures some of the need to be smaller and not as gigawatt scale. But there is a menagerie, a zoo of different kinds of reactors that you will hear about. So I'm going to give you sort of just a matrix to think about. So first, you might divide them in terms of size. Existing conventional nuclear power plants in the United States and elsewhere are typically around 1,000 megawatts, a gigawatt, right? Newer reactors are trying to get smaller, but still like capture the economies of scale on the grid that you need to sort of, if you're going to have a whole site, you may as well make a few hundred megawatts. They're nicely sized for replacing coal plants. We call these smaller modular reactors, small modular reactors. And there are the kinds of very small reactors that we currently operate in the context of like research reactors, right? That might be in the 1 or 2 or 10 megawatt scale. This is similar to like a backup diesel generator, right? Something you might have for a very particular purpose on site. Maybe it's in a remote location and it's the only power, but it powers your whole little town in Alaska, okay? So micro reactors, this very tiny size, small modular reactors, gigawatt scale plants. So that's one factor. What size is your reactor? There are other factors, right? Is it kind of conventionally water cooled, right? And in fact, we use this terminology light water to distinguish water cooled reactors that have enriched the fuel and have left the water normal versus reactors like the Canadian heavy water reactors that have enriched the water so that they don't have to enrich the fuel. Complicated. But all that aside, so the second category, so you've got size, and you want to separate nuclear reactors typically by coolant, right? So Jeff's is sodium, right? Some coolants are gas, like helium, for example. Obviously, the conventional ones are water, light water in the US, heavy water in Canada. We have lead-cooled reactor designs out there. There are liquid salt-cooled reactor designs out there. Some of those liquid salt-cooled reactors have solid fuel, and some of them dissolve the fuel into the salt, and then it's a liquid molten salt reactor, all right? The fuel itself can change. So some reactors have fuel in rods like Jeff that stays static and they're in, just stand there and sit and do nothing. Some reactors have liquid fuel that moves around. Some reactors have pebble fueled. You might see pebble fueled gas reactors. You might see pebble fueled molten salt cooled reactors. And some are even more creative. They might be in a big block, like a big block of graphite, and you're passing some gaseous coolant past that graphite. And inside the graphite, you have tiny particles, triso particles of fuel. That's how you do the pebbles too. Triso particles of fuel. Triso is just an acronym. You'll hear a lot about it. There's a cool article from a few years ago called Power Balls, the new nuclear fuel. And it's very gee whiz. I encourage you to read it. It's in a few cool publications. But basically, little tiny chia seed sized kernels of uranium are coated in some of the hardest material we know, silicon carbide, and then coated again, and then we put them in some matrix like graphite. And those uranium kernels can contain all of the fission products, the dangerous stuff that you don't want to pollute the environment. They can contain them at really, really high temperatures, well past the temperatures of lava, right? And so they sustain and don't do this kind of melting down. Other cool fuels like Jeff's are metal fuel that themselves have a passive safety feature that they expand along with the reaction, reducing the likelihood of the reaction. So as the temperature goes up, the fuel expands a bit, and so the reaction is less likely, so it cools itself back down. This is called passive safety, and it allows the reactor that TerraPower is building, among some other cool passive safety features, to not have all these pumps and whatnot that he described earlier. This kind of passive safety is true across a wide range of different reactors. So I hope I've given you a sort of idea of the menagerie. You want to separate on size, coolant, fuel type, and maybe whether the fuel moves around or not.
Excellent, thank you. I'm going to encourage the Department of Energy to turn that into a cartoon so that everyone can learn about all the advanced reactor types. And so, Jeff and Josh, I want to turn to something that may not be quite as exciting as that. But one of the other features that Jeff alluded to that the TerraPower reactor can do that current light water reactors can't do is this ramping up and down. And so, Jeff, you mentioned the variability of wind, which in Wyoming is a big thing.
I'm told the wind stops blowing there. I've never experienced it myself.
I'm sure at some points it stops blowing. And then in places like California, we've got what everyone loves to talk about, which is the duck curve, which is in the evening as people are getting home from work, the sun is going down, the demand is going up because everyone's cooking their dinners and turning on their televisions. And so the power has to ramp up very quickly.
Right.
I guess, can either or both of you talk about that aspect of advanced nuclear and why that ramping is important and how that works? Like how quickly, for example, can TerraPower ramp up and down? How quickly would it need to ramp up and down?
Yeah, so the reason that the operating fleet that was largely built, 70s, 80s, operates without that sort of, ability to go up and down is because the grid didn't need it then, right? I mean, the way that the power system was made, we had big centralized generation, right? The power would go out in the sort of hub and spoke model, and you would just turn the dials a little bit as the load differed. When we're making the shift to renewables, it's actually fundamentally changing the way the grid works because your supply is now variable, and it's not because it's a broader question about who's turning the dial to make the wind blow or not blow. That's a separate.
That's a different event.
We took a step back and we looked at the reactor and we said, well, what if we thought about it as a heat source? And you had a steady high temperature heat source that was available 24/7. And this is opening up new applications. Katie talked about X Energy, who's the other company who won the ARDP award. They looked at it and said, you think it's hard to decarbonize the electricity sector or the transportation sector? Think about the high temperature heat we need to do things like manufacture chemicals and steel. Right now, the only way you can get to some of those temperatures is to burn met coal or gas at really, really high temperatures. Fossil fuel, there is not a non-fossil fuel option for that high level of heat that has any level of efficiency. So we said, well, if we have this heat source, maybe instead of just using that to generate steam and spin a turbine, we could look at using that heat as a way to run a thermal storage system, which is what we've done. And when we're out talking to utilities and we're talking to other countries, what they're most interested in our reactor, it's not because it's nuclear, it's not because it's has sodium. It's like, you can do baseload carbon-free energy and load follow. That solves so many engineering challenges and problems that we have, right? And so that's what everybody's chasing right now, right? The long duration energy storage, the batteries, the different kinds of batteries. Everybody's trying to figure out, how do you take the sun in California, the solar energy in California, where they're overproducing it in the middle of the day, and shift that energy so you can use it in the evening when the sun goes down, but when people come home from work and are, turn their televisions on and make dinner, right? How do you go from a place like Wyoming when, when the wind stops blowing and you've got to sort of meet the demand and, as people are going about their day. So it's not anything inherent to nuclear that it can't ramp up and down. It's just that you're using designs that were built at a time when that wasn't a feature that was really all that valuable. In fact, the vast majority of energy storage that is currently online in this country is pumped hydro storage, where you pump water uphill when you have extra electricity, and then you run it downhill and run a turbine when you need more. And most of that was built to supplement nuclear when they had low demand at night and they had extra energy. So, just a different time and a different system with different needs. And now, as we're fundamentally changing the grid, as we have to do to solve the climate crisis, there's just different needs for the technology.
Josh, do you want to jump in on this?
Yeah, I think the other thing to add to the complexity of the shift, but also give a good sense of all of the challenges we're facing is the large light water reactors were also built at a time when essentially every state had a regulated utility that just would go to the state regulator and say, we'd like to build this much, and we'd like to have ratepayers pay for it over time. And so at that time, the utilities, they made their money by building more capacity. They would just continue to build more and more to meet demand or anticipated demand. And building it 1 gigawatt at a time was a really good business proposition for them. We started to see parts of the United States electricity system become more open market, deregulated, and you had what were called merchant power producers. And they built on the speculation that there would be a market for the energy that they produced. It would come onto the grid, it would be less expensive, and they would have to either generate revenue from it or not. And if they didn't, they would go out of business. It fundamentally disrupted the proposition of the new types of electricity generation that you built. Oftentimes what resulted was a lot of far less expensive, but also carbon emitting natural gas. And so one of the other things that we saw as a result of that was, particularly as natural gas became both much more abundant and much cheaper at the turn of the last decade, was a lot more nuclear plants, unfortunately, for a period of time shutting down because they just couldn't compete in these merchant markets with natural gas. One of the other really big steps that has happened because of the Biden administration's leadership is the one plant that is retired in the last 2 years, a plant Palisades in Michigan, is in the process of unretiring. I think it's the first plant ever that has started to go through the decommissioning process, that the people that were the company that was decommissioning said, wait a second, we could actually make more money by getting it back online and producing electricity than we can from the contracts that we secured to decommission the plant and manage that. I've been working on climate and energy policy for 20 years now, and we've never had that before. And that is an incredible turn of events that keeps more clean energy online, but also provides a really important signal for anyone on the utility scale to consider, what do we build next? Why do we build it?
So I have one more question I want to turn to, and then I want to make sure everyone's aware that they can ask questions through the QR code, and they can also vote. And so I have the list of questions, and the ones with more votes are rising to the top. And so we'll get into a couple of those in a minute. But I want to talk about actually building some of these plants and then the implications for jobs. And so maybe, Jeff, starting with you, you're building this first plant across the street from a coal plant. What is that? I guess you talked a little bit about the permitting, both in terms of environmental permitting and the NRC permitting. Can you talk about that quickly? And then also, what is the implication for the jobs? Are people moving across the street and getting retrained? Are they, are jobs going away? How's that work?
Yeah, we're building a nuclear power plant. There's going to be permitting required, thankfully, right? So we're going through that process. It's a first of a kind plant. A lot of these, it's a new program at DOE. So there's some growing pains. We're working our way through it. We still feel pretty good that we're going to be able to meet our timeline. But the jobs piece and the economic piece is really important. When we were approached by PacifiCorp Rocky Mountain Power about building this plant, they had actually just announced 4 coal plants in the state of Wyoming that they were closing. And they asked us to look at all of those sites. And so we did something that I don't think had ever been done in the nuclear power plant siting world, which is we went to each of those communities and asked them, do you want this plant? Do you want a nuclear plant in your backyard, right? We did town hall meetings. We answered their questions. We got a resounding yes from all 4 of those communities. We ultimately selected Kemmerer. Kemmerer has the coal plant that's the first of the 4 to go offline. It's a town of 2,700 people. It's in a fairly remote part of the state. The 2 largest employers in that area are the coal plant and the coal mine next to the plant that provides the coal for that plant. So when that plant closure was announced, that community was looking at an existential crisis, right? How do we keep our clinic open? How do we keep our school open? What happens to our property values? How do we keep our community alive when we're losing this many jobs in a short period of time? So 2,700 people in Kemmerer. At peak construction, we will have 1,600 skilled construction workers working on that plant. The town is now wondering what they're going to do to house and keep all of those people in the community. A much better problem to have. We're seeing new businesses come into Main Street. There's a new coffee shop that just opened. I went to the last time I was there, by people who moved in from California out of state, and they see this as an opportunity. There's no coffee shop here. How are you going to have all these construction workers without a coffee shop, right? So they opened a coffee shop. There are 110 IBEW union workers at the coal plant. When our plant is operational, we'll have between 200 and 250 full-time jobs. Nuclear pays better than any other subsector in energy. And that plant's going to be operational for 60 years with an option to extend the license to 80. So we can go to that community and say, we're going to have 200 plus high-paying jobs, union jobs in Wyoming for 6 to 8 decades. Nobody else can make that claim. And I will say this, I know it's very easy to demonize coal, right? Because we know the externalities now of what that burning coal has done to the environment. But we didn't know it at the time. And those guys worked really, really hard to keep our lights on. So we do need to take care of those communities and those workers and make sure that they don't get left behind in the energy transition as well. So we're really excited about what we're able to do in this community. And the jobs piece is really, really important.
Josh, do you want to jump in on?
Yeah, and I think one of the points that Jeff's making that's also sometimes underappreciated is TerraPower is a startup. It's almost unheard of that you have startup companies that are saying, oh yeah, we're going to build with union labor. And the nuclear industry is heavily unionized, which means you have really well-trained workers and good paying jobs that last a long time. And so very early on in our advocacy for advanced nuclear, as we were educating policymakers and others, we started to host events, and we talked to both some of the senior executives at TerraPower and X Energy and said, hey, we'd like to do an event and focus on what's the workforce going to be like. Would you be comfortable if we invited the president of the building trades union that would be building these plants, and the president of the IBEW, the electric workers that will be operating it? And we weren't sure what they would say. And immediately they said, oh, 100% absolutely. So then we went to a senator from a state that had a moratorium on nuclear and said, hey, we're doing this interesting event. It's around nuclear. Would you be willing to host it? And we told them that the unions were participating. And Senator Manchin immediately said, absolutely yes. And also connected, as Jeff alluded to, that these are jobs that could come in and be built at the same location as coal plants that were inevitably retiring, and the communities would survive and the communities would thrive. And so we've seen this as TerraPower has done this in Wyoming, and as a policy organization gotten inquiries from the West Virginia state legislature, from Indiana, from Wisconsin, and from other places saying, what are the things we need to think about from a policy perspective to also encourage the building of advanced nuclear plants in our states, because we like the power and we like the job opportunities.
Dr. Huff.
Yeah, I mean, all of this is precisely true. And in fact, part of the broader look at what it looks like in the United States to build new nuclear. We in DOE released a report last year that indicates that, of the retired coal plants across the country, 80% of them are technically suitable for consideration for nuclear power. You have to cut out some of them for seismic reasons and whatnot. Our assessment is that also because you can leverage the assets in the vicinity, like that transmission that's so hard to build, at the capacity of a few hundred megawatts, having a transmission line, a high voltage power line straight to that location where there used to be a coal plant that produced those hundreds of megawatts. And now there's a nuclear plant. You can save a great deal of money with, in the initial construction and permitting. With that, you can, retrain these workers and ensure the community continues to operate. And, a lot of those communities actually have grown around the coal plant to rely on some of the tax revenues of that plant. And it not only destroys the people who physically work at the plant, and it doesn't, it has real impacts on the workers and the grid, it also has impacts if you lose that tax revenue and that tax base on schools, on medical care, on real fundamental access to primary services in those communities. And so really bringing those communities along in the clean energy transition is foundational in our ability to do a just energy transition, something that really is equitable. I think fundamentally too, you save so much money. We estimate between 15 and 30% of the initial capital costs can be saved through some of these, repurposing of the infrastructure that's already on site, power, water, et cetera.
So we're going to take a couple of these questions from the audience. We're going to be like fast reactors, and so we can get through a few of them.
You mean not moderated?
I failed to cover the energy of neutrons in our distinguishing.
Yes, yes. The little clock here is telling us we're out of time, but I think that there's a couple of really good questions in here. So first is on spent nuclear fuel, and I guess whoever wants to take it can take each question. Spent nuclear fuel always seems to present a NIMBY problem that seems insurmountable. How do we solve that? How do we solve nuclear waste?
The Department of Energy, as of this year, is now doing something rather than nothing. We have restarted a consent-based siting program that was started in the Obama era. It paused over the last administration. It's been restarted. We've released $26 million worth of money to engage communities across the country to find a location to consolidate the spent nuclear fuel across the country that it's DOE's responsibility to take title to. We've begun this process in a way that has worked in Finland and Canada for siting their final repository, which is a much harder problem than finding a place to temporarily store and consolidate. We have to consolidate because right now the spent nuclear fuel is safely stored, but stored across 70-ish different locations across the country, and locations where, those communities didn't necessarily sign up to hold that material for the long term. And it is the federal government's responsibility to take title to it, because you, the American ratepayer, when you bought your electricity, some fraction of that cost, every time a kilowatt hour was produced at a nuclear power plant, that utility paid a fraction of a cent to the federal government to manage the spent fuel. We kept the money, but we didn't take the fuel away from them as was required in the contract. We were required in DOE to take that fuel away in 1998 and didn't do so. We're now on a path to take that fuel, take title to it in the next decade or so.
Excellent. Next question is very timely. Where do we get the uranium from that we're using now, and where is it being enriched? Are there any plans to change the source in the uranium supply?
I'm thinking that subtly that is alluding to the fact that particularly the fuel that the reactor that TerraPower is working on, as well as many of the other advanced reactor companies, is high-assay, low-enriched uranium HALEU fuel that unfortunately is primarily produced in Russia. And so that was a problem that we, amongst many, raised prior to Russia's aggression and invasion in Ukraine, and has become a much more stark challenge. The administration has taken significant steps to restore America's production of civilian sources for HALEU, so that reactor plants can use that fuel domestically sourced. There is a portion of the fuel for conventional reactors that also continues to come from Russia. Particularly other countries in Europe are reliant on that, that steps are being taken to eliminate that need as well.
Yeah, 20% of the enrichment for the existing plants, HALEU aside, right? 20% of the fuel enriched for existing nuclear reactors, which, as we said earlier, those reactors produce 20% of your electricity. 20% of that fuel comes currently from enrichment services and conversion services in Russia. So, the secretary and I and everyone else in DOE is really focused on identifying ways to incentivize more expansion of that capacity in the US so that we can replace that Russian gap. If we can both limit imports from Russia through some import restrictions, and through investment from the federal government, incentivize some competitors in the United States to expand their capacity, then we have a pathway to restoring that energy security that we need.
And the last question, when will we have fusion energy, and what is the pathway there? Jeff, Did you?
Yeah, I have a degree in English again. I'm as qualified to answer this as anyone. No, look, there's been a lot of really exciting advancements in fusion. And, I am confident that we are going to get there. But it's a long way to getting from, the really fantastic things that happened at NIF at Lawrence Livermore National Laboratory to turning that into a commercial power plant. That's not where we are, right? But the continued investment in fusion that I think is really interesting is, the DOE has been participating in these experiments, really driving the sciences. And now you're seeing lots of innovative companies putting private money to try to commercialize this technology. I don't think you're going to make a lot of money betting against innovators in the United States. Like, we do it really, really well. But it's certainly not something that we feel like we can wait on getting fission commercialized, advanced nuclear fission technologies commercialized, because fusion's just around the corner. Might be, but I think there's a long ways to go to take the really important scientific learnings that we're getting, but there's a big gap to turn that into a commercially viable product that can generate electricity.
I shouldn't, but I would love to weigh in on this. I agree completely with Jeff, but I think, it's important to note, like, a comparison between fission and fusion is actually really apt in this scenario. In 1932, it became clear that there was a fission reaction. Lisa Meitner named it for the first time in 1932. By 1942, we had a reactor running, in Chicago. That decade required a great deal of material science and physics and the Manhattan Project, right? Those same scientists did work on, nuclear fusion for weapons in order to get to the H-bomb, right? But we still have not managed to control that reaction, in large part because there are really hard materials challenges and really hard physics problems with controlling the fusion reaction. And, we have demonstrated with things like the H-bomb that we can execute an uncontrolled, super prompt fusion reaction, right? But controlling it in a stable fashion in a material that doesn't degrade because of the incredibly high energy particles that come off of that reaction is a really hard problem. It's harder than fission is as problems go. And you can tell because we've known about the fusion reaction for about as long as we've known about the fission reaction. So it's just harder. It's like holding Jell-O together with rubber bands.
And with that, I'd like to thank our panelists for being here tonight. Thank you.
Sit. I'm just say a few words. Stay down. So, just a couple of final comments here. First of all, I'm betting on decades for fusion. I mean, based on what Dr. Huff said, it's a real hard one. But I agree. But just a few comments. First of all, if we had convened this panel 10, 15 years ago, you would have had a very different discussion. Half of them would have been whining about regulations and costs. You'd never have a TerraPower with an innovative company. It's like an Apple company. A company like Apple actually innovating. Actually innovating, right? Actually innovating, trying things that have never been tried before. A fast reactor, in liquid sodium. It's an amazing thing. You wouldn't have never heard someone from DOE and someone from a small startup talking the way they've been talking tonight and knowing each other so well. You would have never heard the open policy. We're hearing about the opening up of policies. So for me, tonight was a really enjoyable night. So I wanted to thank you, and I'm very, very encouraged. Great. So I want to thank our audience here, the present audience. Thank you very much for coming. We have about 300 people online. Thank you all for coming. Hope you stayed with us the whole time. And again, the panel, two things I would say about the panel. One is thank you for being here tonight. I mean, it really was a great thing, and really we're delighted that you're here. But more importantly, I want to thank you guys for committing to this really important problem. Obviously, you're all extremely enthusiastic about it. You all believe in it. And without people like you, we're not going to get there. So I'm really confident now that with the combination of what all you guys are doing in policy and technology, a little bit of money on the side is great. So let's thank our panel one more time.